So this question looks like it's really going to test us on proof. If you look ahead to part 2, it's a pretty classic example there. Prove that root 3 is an irrational number. That's a proof by contradiction. We've learnt the structure with root 2 and it adapts to root 3 and in fact the square root of any prime number. This first part though, these first 2 marks, Caden claims that 3x is greater than or equal to 2x. Determine whether that's always true, sometimes true, or never true. So first of all, you have to think for yourself, do you actually believe that claim? If x equals 1, it's obviously true. 3 is bigger than 2. If x is 0, it's still true because 3 to the power 0 and 2 to the power 0, they're both 1. So the greater than or equal to statement is still true. But if x is negative 1, 1/3 on the left, and 2 to the minus 1, that's 1/2 on the right, 1/3 is not bigger than 1/2. So suddenly it's not true. So after a little bit of experimenting there, we can say that the claim is sometimes true. And to justify that, we should give one example where it is true and one example where it's not. So I would say if x equals 1, then 3 to the 1 is greater than or equal to 2 to the 1 is true. But if x equals minus 1, 3 to the minus 1 greater than or equal to 2 to the minus 1 is 1/3 greater than or equal to 1/2. That's false. Okay, so sometimes true. We've given one example where it is and one example where it's not. Okay, let's move on to this proof that root 3 is irrational. So it's a proof by contradiction. So the very first thing to do is, well, suppose the opposite. Suppose that root 3 is rational. What does that mean? That means that therefore root 3 can be written as a fraction. So p and q are integers, they're whole numbers. And we can assume that that fraction is in its simplest form. So we can assume that they have no common factors. So that's the starting point for our proof. We've written root 3, we think, as a fraction of integers, and it's guaranteed that we can write them with no common factors. Now we just do some algebra, some manipulation with that, make a bit of space. We're going to square both sides. So we're going to get 3 equals p squared over q squared. We're going to multiply q squared up. So 3q squared equals p squared. Well, p squared is 3 times q squared. So p squared is a multiple of 3. But 3 is a prime number. If p squared is a multiple of 3, that means p itself must also be a multiple of 3. Not too exciting so far, but it's an important step in the journey. Well, if p is a multiple of 3, that means we can write p as 3 times another integer. We could probably call it k or n. P is a multiple of 3, so p is 3 times something, where k is another integer, whole number. Okay, well then we come back to, let's put a star beside this equation so we can refer to it. We're going to come back to that star equation and we're going to substitute p equals 3k. So the left hand side is still 3q squared and the right hand side of that equation was p squared, and we're going to substitute 3k for p. So we've got 3k squared. And let's just simplify that. We've got 3q squared on the left and that's going to become 9k squared when we expand the right. Divide by 3 both sides, q squared equals 3k squared. Now we're going to have a copy of the logic that we had at this stage. Q squared is 3 times k squared, is 3 times something, so therefore q squared is a multiple of 3. And again, if q squared is a multiple of 3, then q itself must be a multiple of 3. And here's where the contradiction happens. So just use a little bit of colour to make the point. At this stage here, we found out that p must be a multiple of 3. And at this stage here, where we've just stopped, we found that q must be a multiple of 3. So p and q both are divisible by 3. P and q have a common factor. 3 is a common factor of p and q. And that's a contradiction because at the beginning we assumed that this fraction was written in its simplest form already and there were no more common factors left in P and Q. So that's why we have a contradiction. So we must say that we have a contradiction, and therefore our conclusion must be that root 3 is actually irrational.